hard to understand. Hopefully, if I show you enough pictures, you'll sort of get what the point is. But we don't know how to do them. And some of them I've been thinking about for 30 or 40 years. Well, 30 anyway. And other people have been thinking about them equally long and haven't figured out how to solve them yet. So I'm showing you a picture right now, which I'm going to describe towards the end of my talk. I'm going to show you this program again. But what it's doing is it's executing a random walk in the plane. A disk is moving around at random until it bumps into the aggregate, and then it sticks to it. So each cycle, one disk is being added somewhere to the edge, and the red disk is the most recently added one. And there's only like maybe between 50 and 100 disks added in now. So I'll show you some pictures later where we have 100,000 or 1 million disks added in. You can see the structure of what's going on a little better. But
okay,
this is the same thing which we don't understand at all.
Yeah, it's 6:35 now, so we can formally start to talk. So Professor Bishop will be presenting random thoughts on random sets.
Okay, well, thank you very much for the invitation. As I was saying, this is a talk about problems and things we don't understand. And so you can ask all the questions you want. I may not be able to answer them, but I can certainly try. If it's about a background question or something, then I should be able to handle it. So I'm just going to pause, stop the MATLAB program for a minute. We'll take a look at that again later on. But let me, I want to flip my laptop into tablet mode. So I'm just going to turn off the video. And hopefully everyone is seeing my screen now. And,
yep, we can see it.
All right. So basically, I want to tell you about the two pictures that are at the bottom. So this one's actually going to go first, and this is the thing I was just drawing on the program, and I will tell you about that a little bit later on. So just to give you a little start, I want to talk about something called Brownian motion. And Brownian motion, we usually start with this. Here's a picture of a Brownian path. It's a random path in the plane, but how do we get to this picture? Usually, it's easier to think about a square grid in the plane. And I've marked the origin here. And at each time, I'm going to flip a coin, or maybe flip 2 coins. I'm going to make one of 4 choices, go up or down or left or right. And when I do that, here I move to the right, then I flip my coins again, and I move up, and then I maybe go right, down, left, down, down, go back up to where I was before, move over. So this is a random walk, and this will produce lots and lots of different paths. In fact, after I take n steps, there's 4 to the n choices, different paths I might have made, because each time I have 4 choices for the first step, 4 for the second, 4 for the third, and so forth. Now, I just made 10 steps here. If I make, say, 100 or 200 steps, it'll look like this. The starting point is marked in red up here. I don't know which is the end point, but it must be one of these. It's probably this point. If that's not the end point, it meant I came up here and then back down here, which is a little bit less likely. And if I went to, say, 1,000 steps, it would look something like this. And here's 10,000, and here's 100,000.
What's the parameter of the random walk?
Well, there's not really a parameter. I'm just taking I'm moving to each of the 4 neighboring points on the square grid with equal probability.
And they are independent of the number of steps?
Yeah, everything is independent. Each step I take, it's completely independent. So I'm just flipping a fair coin or making a fair choice out of 1 through 4 at each stage. Okay. And so in the limit, what we get is a notion of a random continuous path. And so that's what Brownian motion is. I did not prepare a lot of slides on the history or anything technical about Brownian motion. It's named after botanist Robert Brown, who observed particles moving under a microscope. He was watching little pollen particles move under a microscope, and he traced out on paper what they were doing, and they were tracing out a path like this. This is in the mid-1800s. And in, I think it was 1903, Einstein, in his miracle year, when he also published his most famous papers, he explained Brownian motion as these little pollen particles being hit by even smaller invisible particles, molecules. And this was causing the random motions of the visible particles. And in fact, not only did he, do this sort of qualitatively, he actually quantified the mass of those particles that were hitting it based on the motion. And that way he was able to compute the weight of the molecules, and that actually led to the most accurate computation of Avogadro's number up to that point. Now, you don't have to do this on a square grid. Here I've sort of drawn the same thing on a triangular grid. I didn't put the triangular grid in. It would look something like this. If I were to draw a triangular grid, that looks like a bit of a mess. But if I did random walks on a triangular grid, here's a 10-step walk, and here's 100 steps and 1,000 steps and 10,000 steps. And then the limit, it looks pretty much exactly the same as the walk on the square grid. And you can do other things. For example, instead of just choosing a finite number of steps, you can draw a little circle around where you are and randomly choose a point on that circle. And then you draw a circle around the new point, and you randomly choose a point on that. Now here, the second point is I've jumped right back to where I was almost the same. That's a little bit unusual, but I didn't cheat. I just let the random number generator do what it wanted to do. And then you go back, and it lands almost exactly on that same point. That's kind of a coincidence. The third time, we do something a little bit different, and the fourth and the fifth, but each time I'm just drawing a circle around the current position and randomly choosing a point. And I can keep going, and there's 100 steps and 1,000 steps and 10,000 steps. And in every picture, once you do enough steps of these random walks, you basically get the same limiting picture. And this limiting picture is what we call Brownian motion. And so it's actually a theorem called Donskoy's invariance principle that whenever you do a random walk, which is IID, that just means that you are taking identically chosen steps. They're independent, so each step doesn't depend on anything else you've done, and they're all identical. That is, you're using the same model, either always going up, down, left, right every single time, or you're always stepping on the triangular lattice, or you're always stepping on a circle, but you do the same thing every time. You will always converge to Brownian motion, this continuous limit.
I have a question.
Sure, go ahead.
Does this has anything to do with central limits theorem? Because this seems
Yes.
very like central limits theorem, but
right. So there's this thing called Brownian motion. I mean, I'm leaving out a bunch of technicalities, but when you run a Brownian motion for some time, if you run it for time 0, you're at the origin. That's where you start. If you run it for, say, 1 second, there's a continuous distribution of where you might be. You're sort of very likely to be near the origin, but there's some chance that you're, moved about distance 1 away. And there's a very small chance that you might have moved a very far distance, like 100 away. That's pretty unlikely. So there's a probability distribution that's centered at the origin and dies off as you move. And basically it's the Gaussian. Now, there's a constant here, which I won't put in. I think it's pi or root pi. And so this is the central limit theorem, basically. The central limit theorem is saying that if you take lots of little tiny steps and add them up, it'll approach a normal distribution. And I've just said, well, these little tiny steps are converging to something called Brownian motion. So the way Brownian motion moves through the plane is it's very erratic. It's sort of moving around at random. But if you ask what's the probability that you've gone a certain distance in a certain time, you can predict that probability using Gaussian function. And so that comes out of the central limit theorem. So you're quite correct about that.
Why does the mean have to be 0?
If it's not, if you, for example, you stepped, in one direction, suppose I went to point 2 with probability 1/2, and I went to 1 with probability 1/2. Well, I can do that. I can do that jumping back and forth, but on average, I'm going to take 2 steps to the right for every step I take left. And so after n steps, the Brownian motion, the random walk I get, it'll drift off to the right because I'm sort of like pushing it to one direction. So you can define a random walk like that. It just will sort of vanish from your view. It'll drift off towards infinity. The mean value saying that you're, on average, you're staying where you are. So when you take the jumps, you're sort of equally likely to go in any direction. That keeps the random walk and the limiting motion centered. So you're likely to come back to the origin infinitely often. At least you're likely to come back to a neighborhood of the origin infinitely often. Okay. So otherwise, you get a Brownian motion with drift. which can be interesting. I mean, people do study that, but the Brownian motion with no drift is sort of the more natural one. Okay.
Okay.
Now, those are all terrific questions. So here's the first, I mean, lots and lots of things about Brownian motion are known. It's been studied for over 100 years. I mean, Einstein wrote his paper on it, I think, in 1903. It was mostly physics. It wasn't really rigorous in the way mathematicians would think of it, but Norbert Wiener in the 20s put it all on a perfectly rigorous basis. That's why one of the reasons we study things like measure theory and do infinite dimensional vector spaces and functional analysis and study advanced math. One of the applications is to make this notion of Brownian motion perfectly rigorous, and it's a well-defined mathematical object. One nice theorem about it, well, there's several. Let me just give you some of the highlights. If you run the Brownian motion forever, like you just keep running it for infinite time, it will eventually become dense in the plane. No matter what disk you choose in the plane, eventually, if you wait long enough, the disk will visit that. And that's true no matter how small or where this thing is located. So the Brownian motion eventually visits every place. Well, if we only run it for a finite time, like 1 second, maybe starts here and ends over here. And it's a continuous image of the unit time interval, so it's a compact set. But it's a kind of complicated compact set. We can prove that it has 0 area. That's a theorem about it. If you happen to know anything about fractal dimensions, I wasn't going to get into that, but it has fractal dimension 2. So it has 0 area, but it's almost like a positive area set. It's almost like a 2-dimensional set. Later on, we're going to get back to the complementary components. So in this picture, you can see that there are some pieces of the plane which are separated from the outside by the Brownian motion. So there's all these little components here which are separated from the outside. And there's actually infinitely many of those. And one of the problems I'm going to tell you is about the shape of those things. They're kind of mysterious. We don't know a great deal about it, but there's infinitely many of them that we can prove for sure.
Quick question.
Sure.
This is only kind of half form, but like, does the geometry of the plane matter too much? Like, if we instead did this on something that like loops back around itself like a sphere, would that change?
If it's
any
2-dimensional, it's going to be basically the same.
Okay.
There, you can have Brownian motion on the real line, which is different. If you have Brownian motion on the real line, it actually visits every place because the Brownian motion basically wanders back and forth. And if you wait long enough, it'll visit minus n to plus n. And because it's continuous, it has to fill in everything in between by the intermediate value theorem. If you're in higher dimensions and you start a Brownian motion, even though it's centered at the origin and has this mean value property, it will still wander off to infinity, turns out. In 3 dimensions, a Brownian motion will drift off to infinity even without you pushing it. So the plane is kind of special. The plane's the one case where the Brownian motion keeps coming back near the origin infinitely often, but it does not visit every single point. It only visits a dense subset. So the plane is kind of a particularly interesting case in that sense. Okay? All right.
Thank you.
Now, one thing, that the Brownian motion doesn't look very straight here. I mean, I don't see any line segments. And this is actually a pretty tough theorem proved by Robin P. Mantle back in the 1990s, is that if you look at this compact set that the Brownian motion traces out, he proved there are no line segments in it. If you take any 2 points and draw a line segment, the Brownian path does not cover that segment. There's something that's left out, okay? But what he couldn't prove was, does it cover a finite length curve? If I take 2 points in the set, is it possible that I could connect them by a finite length curve? Now, the Brownian motion itself is a 2-dimensional thing. It has infinite length. So if you tried to follow the Brownian motion all around, that would definitely be an infinite length path, but maybe you could take shortcuts. I mean, maybe you just sort of not go in the same order, but just cut it off. And so that's an open problem. Does the Brownian motion, does this set cover a finite length path? And we don't know that. In terms of the grid, if we don't want to take the limit, if we're just thinking of this as a sort of a large random walk, if I take n squared steps, we can prove that the cluster we get is about n. It's the square root of the number of steps you take. And so if I took 2 points here, like one over here and one over here, what does it mean to have a finite length path what it would mean is that in the grid, could I connect these by a path that was length of about n, like maybe 100 times n? Or do I need a higher power? Do I need, like 1.2? That's saying that the curve connecting them would be kind of a fractal, that its length is growing larger than the distance between the endpoints. And there's some things known about this, but we don't know if any 2 points are connected by a rectifiable path. One thing we do know, this is a very famous theorem of Greg Lawler and Wendell and Werner and Oda Schramm, based on what's called SLE technology. Wendell and Werner won the Fields Medal, not because of this particular theorem, but because of the techniques that they used to prove this theorem. One thing you can do is just trace along the outside. So if you just went along the boundary of this, I'm just trying to trace along the outside boundary of this. And you want to go from a point over here to a point over here that are about distance n apart. They proved that the length of this curve that connects them along the boundary edge is n to the 4/3 long. It takes n to the 4/3 step. So I wrote down the wrong constant here. Sorry. N to the, I'm sorry, I'm having a hard time writing on my tablet tonight. N to the 5/4. And this was a big success. So there are paths, namely what we call the frontiers, the outer edges of these connected components, and they are basically fractal type curves. And if you run the random walk and you're trying to connect points that are about distance n apart, you can't connect them in a straight line, which would only take n steps. You can't even do something which is 1,000 times n. You really need n to a larger power. And so this was a conjecture of Mandelbrot. If any of you have heard of the Mandelbrot set, it's named after Benoit Mandelbrot, who wrote a book on the fractal geometry of nature. And one of the conjectures he made is that these outer boundaries, that when you trace the outside of a Brownian motion, its length should scale like 5/4. So he had conjectured this back in the early 70s or late 80s, but it took about 20 years before mathematicians were able to prove that this was correct. Now, if you don't stick along the outer boundary, but you're allowed to sort of plunge through the middle, you might hope to have a little shorter path. And this is what we're wondering if you can get it down to being one-dimensional. There's some recent work in the last 5 years or so by Zhang, which shows you can get the 4/3 down to 5/4. 1.25 is a little bit less than 1.33. But that's the best we know. And the question is, can you get this all the way down to 1? And we just don't know that. That is a tough open problem. If you can think about that, find a way of doing it, or either for the continuous Brownian motion limit or just these analogous questions for the random walks, that would be terrific. We would love to know the answer to that. Let me just show you a couple of simulations. Here's my starting point. I've done a 200-step random walk, and suppose I want to say come down here, somewhere around here. Well, it looks to me like the shortest path would be something like that, connecting them. Maybe I could come down, this way. There's a couple of paths that have the same length. Now, if I want the computer to do this, I don't want to have to count how many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think, steps. If I want the computer to do this, there's a actually fairly simple way to do that, which is called the minimal spanning tree. So if I just go back a picture, I'll show you what I told the computer to do. What I said was connect each so for each take everything that's adjacent to the starting point and connect it up. And now everything that's connected to one of those points, you add them in, but don't form any loops. If something is already connected, you just connect up one at a time. And when you do this, what you form is something called the minimal spanning tree in graph theory. And it's pretty easy to compute the minimal spanning tree, and that's what I've done here. And the point is that if you start at a vertex and you just follow the spanning tree back to its root, that will be a shortest path. You're guaranteed it. And so I can have the computer do this, and it finds the shortest path for me. So I don't have to do it by hand. I can do it by hand on a picture like this, but when we get to a little bit bigger picture, like 1,000 steps, and I want to find the shortest path, it's easier for me to let the computer do it. There was a question?
Yeah, yes. Are you really talking about the algorithm question about shortest path or minimal spanning tree? I thought those are two different algorithm question.
Yes, well, I'm really just interested in finding about when I have 2 points in my cluster, approximately what's the shortest path between them. So the minimal spanning tree
The minimal spanning tree not necessarily cover the shortest distance between 2 points.
Yes, but I'm interested in it will give me the shortest distance to the root. So yeah, if I want to go from here to here, it's not helpful. But when I connect to the root, it is always giving me the shortest path from any vertex to the root. That will be correct. Now there'll be lots of shortest paths, and it's only picking out one of them, but it will pick out one of them.
Okay. Okay.
Yeah. So here, for example, is a shortest path between a point up here and a point down here. Now the question is, as the grid gets finer and finer, is this connecting path, is this going to converge to something of finite length, a rectifiable curve, or is it going to converge to some kind of fractal curve whose fractal dimension is bigger than 1? And I don't know. I mean, nobody knows as far as, I mean, this is an open question. Here is a plot of the size of the cluster. So this is the number, this direction is the number of steps I took. This is a log plot. So this is actually like e to the 7 steps here. And this was, here I just randomly chose a point in the cluster. So my cluster has n steps. So its diameter is about root of that. And I just took the origin and some point that was, I look for the shortest path that connects the origin out to the circle. So I have the origin, I draw a circle, I have my cluster, and then I'm looking for the shortest path that connects the origin through the cluster to a point on this circle. And I did this for thousands of examples, and I plotted it. And I plot the log because then if it's growing like n to the alpha, and I take the log of that and divide by n, well, the alpha comes out, and the logs cancel, and the slope of that line should be what the power is, alpha. And in this case, it turned out to be 0.0445, which is very ambiguous. It's very close to 1. It's only 4% higher than 1. So is this showing that I'm actually going to a fractal whose dimension is a little bit bigger than 1? Or is it showing it's going to 1 and I've just made some experimental error and my experiment isn't big enough? And if I waited longer, I would get even smaller number, something closer to 1. I don't know. So this is something we just don't know the answer to this. So
of rounding off error.
It could be. It could just be a rounding off error. I did have a student as an undergraduate honors thesis a few years ago do some larger simulations of this. He also got a number that was similar. It's actually a little bit smaller. He might be like 0.029 or something, a little bit smaller. However, he was actually computing the shortest paths not as efficiently as he could. And so his examples were maybe clusters of about 1 million or 10 million at most. And I think we really need to get into the billions or hundreds of billions and see what happens. I would feel better about that. So I haven't done those experiments yet. That would be another good project for someone someday. And so this is a problem. So if you have this Brownian trace and you want to connect 2 points, like this one over here to this one over here, how does that grow as a function of the number of steps in the random walk here? Or if you're in the continuous case, how big is it in terms of dimension? And there's lots and lots of related questions. So for example, I'm not requiring that any 2 points can be connected by a rectifiable path, just that there is some pair of them. So I could ask, well, what's the best I could do what's the worst I could do? Are there 2 points where I definitely cannot connect them by a rectifiable path? I'm not sure. Probably there are. What does this path look like? I'm going to show you a blow up of this section here and this section here, 2 different sections. When the Brownian motion is kind of dense, the curve goes through in a pretty straight way. It looks like it's almost a vertical line. It looks pretty good. Places where the Brownian motion is kind of thin, the path has to twist quite a bit because it's not allowed to leave. And so it has to follow it. If it does a lot of twisting like this, it's not going to be rectifiable in the limit. But if it looks like this most of the time, then maybe it does have nice tangent lines. Maybe it's a nice rectifiable curve in limit. Which is the more common picture? Don't really know. Can make some guesses, but we don't really know that one. Okay, I was going to go on and tell you another problem, which is probably harder than the first one. Are we ready to go on, or do you have a few questions about what I was just telling you? Okay, let's go on a little bit further. So this has to do with these complementary components. You remember when we run a Brownian motion, we have this random path like this, and it's cutting the plane up into pieces, right? So there's this one big unbounded component out here. It's a compact set. So there's one connected component out here, and then there's other connected components. I mean, here's one, and let me use a different color. Here's another color, and here's another component here, and all these ones. And these components can possibly touch each other. For example, this component touches that one, and it touches that one, it touches that one. This component here does not touch this one over here. They don't come in contact that I can see, but this one in the middle does contact that one, and this one touches the outside. And that component touches that, and that one touches that one, and that one touches that. And we can draw a graph where each vertex is one of these connected components, and we connect them if they share some boundary. And the question is, what's the structure of this graph? We don't know what the structure is. What's an infinite graph? It has infinitely many vertices. That we know in the limit. We also know in the limit that each of these components will touch infinitely many other ones. And so this will actually be an infinite graph that has infinite degree at all the points as far as I know. But is it connected? Can you go from any component to any other one by just moving across ones that share a boundary component? Is it a connected graph? That's an open question. So this is a very famous question of Wendell and Werner. I mentioned he won the Fields Medal, I think around 2000 or 2004. And I think he's thought pretty hard about this, and we don't know the answer. We can do some experiments like we did before. Here is a trace of a random walk of 200 steps, and you can see all the components here. I'll color them in on the computer. Here they all are shown in different colors, but I'm interested in connectivity, which ones are connected to which other ones. And mostly I'm interested to know which ones are connected to the outside. So there's this one component outside where infinity lives, and then it touches certain components. But there's other ones like this one, which it doesn't touch. There's a barrier between them. And so I'm going to color the components in this way. White is the outside. Light blue is everything that touches the outside. Okay. And then dark blue is everything that touches light blue, but has not already been touched by the outside. So in this case, there's two layers. There's the outside, the things that touch the outside, and then the things that touch those. And that's everything. There's nothing else. But if we had a bigger graph like this, we have more layers. Here, yellow touches the outside, then light blue touches the yellow, and then dark blue touches the light blue. And we can get larger and larger examples. I've drawn a couple here. Here's a couple of 10,000 steps. And you can see basically red and orange is on the outside. And the more blue you get, the more steps you are on the inside. And what we want to know is basically how far in do we go? Now, Werner's conjecture is that is there a big component like this one? Here, let me try to. What Werner wants to know is in the limit, can every component like this one be connected to the outside component in a finite number of steps? Now, the contrapositive, the opposite of that, is that there's some component here which you cannot connect to the outside. So you can connect it to other things, and the outside can be connected to other things, but they never touch. So whenever you're on this inside component and you try to look at all those things that it's connected to, you can sort of grow a component of this graph, but that graph never touches the graph that you get when you start growing from the outer component. So you can start on the outside and work your way in, and start on the inside and work your way out. And the question is, do these always have to connect up? And Werner conjectured, yes, they always have to connect up, but we don't know that. It's possible that there's some component that has a barrier around it that you can't get across. And so I was doing these experiments to sort of see, did I ever see this in any pictures? This is about the worst picture I know. You notice over here, there's a component, this light blue one, which I'm circling. It is pretty big. It's about 10% the size of the whole component, and it's 12 steps in. So the total depth is 20 steps. The dark blue is 20 steps in, but this is a 10% component. It's almost as big as the whole thing, but it's pretty far in. It's 12 steps in, and I needed to go a 50,000 step walk to find this one. Here's an even bigger component in the red, but it's not as far in. It's only like, I think like 5 or 6 steps in. There's 1, 2, 3. I think it's the only 3 or 4 steps in. So it's not very far from the outside component. And we can make a graph of how big the components are versus how many steps they are from the outer component. And what Werner's conjecture is that this goes down to 0. That the more steps you are in, the further in you are, the smaller you have to be. Because what we don't want is that there's a big component, big in the size of diameter, which is sort of infinitely far away from the outside. He says that that will not happen with high probability. And so basically we want to show this thing goes down. Well, when we collect the data, we do thousands of examples, it goes down. But we don't know how to prove that.
I have a question.
Sure, go ahead.
Right. So you're saying in the limit, but I don't really understand what that means, because when you said before, if you let the Brownian motion run forever, it visits every neighborhood infinitely
Yes,
often,
but we're
right?
only going to let the Brownian motion run for 1 second. So this is going to limit on the Brownian motion the image of the interval from 0 to 1. So it's a compact set. So we're only running it for a compact amount of time. So what we get is a continuous image of the unit interval. Continuous image of 0, 1 is a compact set in the plane.
Okay, thank you.
You're right. If we ran it forever, there'd be no complementary components, but we just run it for a finite amount of time. Yeah, so we don't know how to do this one. We're just stuck. Yes, if you figure out how to do this, I will meet you in a dark alley somewhere to hear your solution. Now, even for the random walk, it would be interesting to know how deep is this graph. If we run this thing on the grid for n steps, about how many layers in can we go? And I plotted that again here. It looks like a power function. If it's a power function, if I do a log-log plot, it should become a linear plot. And I do a log-log plot, it looks like this, which to my eye looks pretty linear. And the slope, according to MATLAB, is 0.35774. And so it looks like the depth, when we do a random walk on n steps, we can expect about n to the 0.36 layers from the outside to the innermost level. Don't know how to prove that. That might be very reasonable. Probably almost no one in the world has tried to prove that. I don't know if anyone has worked on that, so that might be a doable problem.
What is the motivation for wanting to prove these kinds of open problems besides, just wanting to prove open problems? Like,
well, Brownian
like,
motion is one of the most interesting things in the world. And so we claim to know lots and lots of things about Brownian motion. I mean, it's used everywhere. It's used in differential equations. It's used to predict the stock markets. It's used in turbulence. It's used, in all kinds of physics and chemistry and biology. And so as mathematicians, we'd like to answer any question anyone may ask about it. Now, it could very well be that no biologist or finance person will ever wonder about these components, but these are pretty basic questions. What are these components? What they look like? How are they connected to each other? These are things which we feel we should be able to do, but we can't.
okay,
There's been tremendous progress. So it's sort of like proving yourself, like proving that our techniques are good enough. These are just some questions which our current techniques, I mean, many things have been proven in the last couple of years. Like I mentioned this, if you take the frontier of the Brownian motion, that it had this fractal dimension 4/3, that had been open for 20 or 30 years, and it was solved. I had contributed a little bit to that myself. I was very proud. I and some other people proved the dimension was bigger than 1 plus epsilon, so strictly bigger than 1. We were very proud of that paper until these other guys came along and proved it was actually 5/4 or 3/4. They actually got the right number. That was a better result. But problems like this are a way of testing our methods, our understanding. And so that's probably the main reason.
okay, that makes sense. And then just another quick question.
Sure.
Did that proof involve taking anything from complex analysis from the complex plane, or are we just—
Yes.
Okay.
I'm going to get to that next, actually. before I talk about the final thing, which was the diffusion limited aggregation, I just want to talk a little bit about harmonic measure. It's not a huge part of what I'm going to say next, but it's very much related, and I thought it was worth throwing in a couple of terms. So we're going to take a polygon in the plane in honor of our guests from Indiana. I made it look like their state, and I'm going to start a Brownian motion in here, and we run the Brownian motion until it runs into the boundary someplace, and then we run another Brownian motion until it runs into the boundary someplace, and what you get is the probability that it will hit. I can, given a piece of the boundary, I can ask, what's the chance that a Brownian particle will first hit the boundary here as opposed to anywhere else? That defines what we call the hitting distribution on the boundary. And so here I've chosen Illinois as the boundary. If you're at my talk, I gave a talk at Indiana a couple of weeks ago for the math colloquium, and I'm reusing these slides. So if you were at that talk, this is a repeat of something. And so, and for my base point where I'm going to start the Brownian motion, I chose Bloomington. Seemed like a pretty good idea. And then we run a Brownian motion here, and I've done this 10 times. So this Brownian motion almost hit here, but it didn't quite. It went on and eventually hit up here. And then I run it again, and now it does run into in Illinois. And then it sort of seems like this is the closest part of the boundary. It should hit here quite a bit. And the next couple of hits all do occur here. And I think I do 10 of these. And then I say, oh, I'm tired of this. Let's just jump to 100. And so here, the red dots indicate 100 distributions. And the ones that were on Illinois, if you count them up, I believe it's 30 out of 100. So the probability of hitting Illinois, if you randomly start walking from Bloomington, is about 30%. Now, if we started somewhere else, that probability would change. So if I started here, this is Indianapolis, and I do the random walk starting here. Again, if I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I jump up to 100. Now looks like I have 34 out of 100. So a little bit higher chance of hitting Illinois than I did before. But I only did 100 samples, and 30 and 34 are pretty close together. So maybe it was just experimental error. How can I be certain? Okay. Well, there's faster, better ways. If you were actually watching my code to create this picture, it took about a minute or so because it was taking all these little steps, and it would take actually a couple, like tens of thousands of steps before it eventually run into the boundary because I was taking very small steps. There are several faster ways of doing this. One is, instead of taking a little walk on a grid that takes a long time, we can use the observation that if I draw a circle around this point, the Brownian motion turns out to be rotationally invariant. So I'm equally likely to hit here as I am to hit here. So the chance of hitting only depends on the length of the arc, not where it is. It's rotationally invariant. So the Brownian motion, if I start it from here and I let it walk, it's equally likely to hit anywhere on the circle. So instead of running this walk until it hits, what I do is I just choose one point and jump straight there in one step. Then I draw a circle around that, and I choose a point at random on that, and I jump to there. And if I let the computer do that, it looks something like this. I draw my circle, I choose my first point. Then I draw a circle around that, and I choose my second point. And then I keep doing this. And this wanders around and eventually gets very close to the boundary. And once it's within like 0.001 of the boundary, I stop. And the neat thing is that if this was like a 1x2 rectangle and I was taking steps that were size 1 over n, so I was using a 1 over n grid, the number of steps it takes to reach the boundary on the grid, it takes about n squared steps. But this circle method, we can prove only takes log of n steps. So if n is like 1,000, then this takes 10 to the 6 steps, and this takes like 10 steps. It's 100,000 times faster to do the circling walk. So that's one thing you can do. You can actually do even better than this. There's even a faster way to compute harmonic measures than this. This has to do with conformal mappings. And so for the next couple slides, I have to assume that you've had the complex variables course. If you haven't, don't worry. in about 5 slides, I'll be back to not referring to it anymore. But one of the things that you usually get to at the end of a 1 semester course is the Riemann mapping theorem that says that if you're given a simply connected domain, like something bounded by a polygon, there is a 1-to-1 analytic mapping, a 1-to-1 holomorphic mapping that takes the disk to this domain. And you can make the origin go anywhere you want, and you even have a little bit extra freedom beyond that. And the other secret is that Brownian motion is a conformally invariant. So if you start a Brownian motion here, and you take its image over here, it's still a Brownian motion. There's a little proviso that it runs a little bit faster or slower, but the places it goes is exactly the same. It just moves a little bit faster or slower in the image than it did in the disk. On the disk, we know harmonic measure, the chance that you hit an arc is just its length. Well, it's length divided by 2 pi, the total length. It's the percentage of the circle. So if you take a half circle, you have exactly half a chance of hitting the top half of the circle and half a chance of hitting the bottom. And so if you take an arc over here and you compute what its pre-image is here, you see, well, how much of the circle is that? That gives you the harmonic measure. And then the conformal invariant says, well, the chance that a Brownian motion will hit it over here is the same as it would have hit its pre-image arc here. And it turns out this is a much faster way of computing it because we have fast algorithms for computing Riemann mapping. I might just mention Riemann mapping, of course, is named after one of the greatest mathematicians who ever lived, Bernard Riemann. This was part of his thesis, where he also invented Riemannian geometry and did a bunch of other things as well. He did not actually prove it in the generality we state it today. The version that we use today, which says that for every simply connected domain in the plane, except for the plane itself, there's a mapping. This is actually due to William Osgood. He's a professor at Harvard. He was the one who dealt with when the boundary is very, very rough, when it could be a fractal curve. They didn't use the word fractal back then, but basically when the curve could have weird properties, like not be locally connected or not have, you could have positive area. I mean, he was the one who realized that the boundary of a simply connected domain could be a very weird object, but he overcame those difficulties. And there's a history article by Walsh in which he basically claims this was the first proof by an American mathematician that sort of was up to the standards of European mathematics at that time. So this actually appeared in issue number 1, volume 1 of the Transactions of the American Math Society. And so the Riemann mapping theorem is something we can sort of claim for ourselves here in the United States if we want to, although he was actually trained in Germany. So at that time, all the top American mathematicians went to Germany, or maybe England or Italy or France, but a lot of them, the German, especially people like Klein, were very, very influential in training the first generation of American mathematicians around the turn of the century. In any case, here, for example, I split up the circle into 20 equal places. So each of these arcs is 5% of the circle. So each of these has 5% chance of being hit. And here are their images over here. So this arc here has a 5% chance of being hit from that center. So does this little arc here. Okay, so even though this arc is much bigger, it has the same chance. This one is on an inward-facing corner. Inward-facing corners tend to be much easier to hit. Let me try and see if I can blow up this picture a little bit. Here, for example, the end of that arc is actually made up of 2 of these arcs. So the tip, there's a picture here. I'm sorry, I'm trying to draw this. There's a picture here. You have this blowing up this piece, or this arc, that's 10% of the harmonic, 10% of all the Brownian motions coming out of here will hit right there at the end of that. And an equal number, 10% will hit this huge area here. So inward pointing corners like this tend to absorb a lot of harmonic measure. And things that are kind of far away, like, you know, this is a huge arc Euclideanly, but it only gets 5%, much less than these arcs over here. So harmonic measure is sort of related to arc length on the boundary, but not very directly. And this is something I myself and other people have spent a long time trying to figure out.
I have a quick question.
Sure, go ahead.
So this Riemann mapping theorem, is it like constructive? Can you give me
Yes.
the map? Okay.
I could give a whole lecture. In fact, my last math lecture for the math club at Stony Brook was maybe 5 or 6 years ago. and it was about how to actually write computer programs to compute it. So these programs, I didn't draw by hand. I mean, these pictures were drawn by a computer program in MATLAB. And so, yes, this is something we can construct. One of my own papers from about 10 years ago gives the most efficient theoretical algorithm for constructing the Riemann mapping. So there's a whole story you can tell there. Here, for example, is a picture of the Brownian motion on the disk. And here's the image of the exact same Brownian motion mapped forward. You can see it sort of has the same shape. You know, you have this little bit here that corresponds to this bit, and it comes down here. That's like coming down here. Then you turn. So it's the same Brownian motion. You're just looking at its image under the map, and the same here, and the same.
I have a question. So
sure, go ahead.
Since it seems like the corner can absorb a lot of
Yes.
like Brownian motions.
Yes.
And can we construct a corner such that it has like atom weight? That means that
there are no atoms.
Oh.
So you cannot do that. But how much you can concentrate it, that's a very, very interesting question. And I took out the slides where I was going to talk about that because I wouldn't have enough time to finish. But if you like to, I can come back and give you an entire talk about that. There's a huge history about that question of how concentrated can you make harmonic measure. And maybe after the talk, if you want to ask that question again, I can give you a more detailed answer. But if I start on it, I'm likely to take an hour. I mean, I can tell you a lot about that. But I'm sort of steering away from it. Just for our Illinois question, if we map the disk so the origin goes to Bloomington, and we want to know what the chance of hitting Illinois is, then basically we want to connect these corners up and ask, what's this angle here? What arc does that correspond to? And when I let the computer do it, it's this. And the chance of randomly hitting Illinois from Bloomington turns out to be 0.31246. And I could compute many more decimal places to this if you wanted. And this only took a fraction of a second on my laptop, whereas the random walks took about a minute just to do 100 of them. And so this is a far, far better method of computing harmonic measure. If I do it from Indianapolis up here, the answer is 344. And so what you see is the chance of hitting Illinois is a little bit higher from Indianapolis, but not much, only in the second decimal place. It's almost the same chance of hitting it. If I were to start from someplace over here, then I'm much more likely to hit one of these corners, and my chance of hitting Illinois would be much smaller. Okay. So in general, the starting point, if you think of this probability as being a function of where the base point is, it turns out to be a harmonic function. So that's why we call it harmonic measure. It's the harmonic function, which is 1 on the set you're interested in and 0 elsewhere. So if you want to think of this as a differential equation, the boundary values are 1 on Illinois and 0 everywhere else. And then you're trying to solve the Laplace's equation, find a harmonic function whose boundary value is 1 along here and 0 everywhere else. That's an alternate way of computing harmonic measure. That's why it has the name harmonic in it, is because of its relationship to harmonic functions. Okay. Now, finally, the last topic I wanted to talk about was this thing called diffusion limited aggregation. It's a growth model in which we add disks according to harmonic measure. And now you know what that term means. Let me see if I can run the program that I was trying to run before. I have to flip I was using my computer tablet form. Okay. So what we're doing here is we started with a disk in the middle. Unfortunately, I'm running MATLAB. I don't have the ability to highlight with my pen anymore. But what we do is we're going to take a particle coming in from infinity. Now I can't on the computer say start a particle at infinity because the computer doesn't know what infinity is. But what I do is I choose a big circle that surrounds the cluster. Whoops. And I choose a point randomly on that. And then you can see I'm starting my random walk here. And I'm not taking little steps. What I'm doing is each stage, I'm computing how far I am from the boundary and then taking a step that's big. So I'm using this big steps version of Brownian motion. And so I simply start a Brownian I have a disk moving. Its center is moving according to Brownian motion. I run it until it slams in to the existing aggregate, and then I stop it. And the most recent disk is colored red. So the red disk is the one I added last, and I keep adding more and more disks onto it. And this is something called diffusion limited aggregation. Aggregation means I'm aggregating, I'm making things bigger by adding to it. And diffusion means I'm letting the particles move by a Brownian motion. I'm diffusing them in the plane. There are lots of other growth models you can use. For example, you could attach a disk anywhere there was a free space for it to go. Harmonic measure, because we're sending it from the outside, it tends to stick to the outside a little bit more. And it's a little bit harder. This would probably, I mean, I've set it to run 1,000 disks. That would probably take a couple of hours for it to finish at this rate. So I'm not going to let this run. Let me, we can come back to this in a few minutes. I'll let it run in the background. We'll see how far it's gotten in about 5 minutes or 10 minutes. Let me go back to my slides. Question about this first?
Yeah, can this be used to study crystal? How crystal is?
So you can actually go on the internet and you can find pictures of aggregates which are grown in fluids, mostly in 3 dimensions, but also they do grow them like between 2 glass plates. And they end up, the pictures look very much like this. So here's a picture with, I think, 100,000 aggregates. Let me show you how it's built up. So remember, the idea was we have a fixed disk. I draw a circle. I start a disk on it. I let the disk wander around until it hits, and then I fix it. And then I have 2 disks. Then I choose another random starting point. I let it wander around until it hits one of the disks. Then I get 3. Then I draw my circle, choose a random starting point, let it wander around till I have 4 disks. And I keep building up in this way, larger and larger things. But it starts to get interesting once you get up to, say, this is 100 disks. And here's 1,000 disks. And here is 10,000 disks. And now you can see it's starting to look like some kind of fractal kind of object. And if you do this on the computer like we're doing it, or you do it with certain kinds of ions in a fluid, the pictures look almost the same. So this is considered a pretty reasonable model for certain physical processes. Now here, I've just taken all the black disks and I colored them depending on the numbering. So at the very center are the low numbered ones, the ones we added first. And the red ones are the most recent ones we've added. And what you can see, of course, is that the old disks are near the center. And as we add new ones in, they tend to stick to the outside. Okay, this is like the corners for harmonic measure. We saw a picture like this, where the particles, like in corners like this, had a lot of measure, but corners like this didn't. And so here, if you're wandering in here, the chance of sticking to one of these things is pretty high. But the chance of coming in here and sticking in here is smaller. Now, there are some red disks here. You can see them. So occasionally a particle will get in here, but most of them are sticking to the outside. And the basic question is, how fast is this growing? After I've drawn n disks, how big a cross is this? We don't know. Well, mathematicians don't know. Here's 100,000. If you ask physicists, they claim they know the answer to this, to like several decimal places. But as far as the mathematicians are concerned, they're just guessing. There's no proof that they know how quickly this grows. Now, we can do numerical experiments. And if we, again, this is a log-log plot. So what we're expecting is that the diameter will grow like some kind of power, n to the alpha. And so if we plot the diameter, the log of the diameter over the log of n, so if we took this log over log of n, the alpha should come out and the logs cancel, and the slope of this line should tell us the rate of growth. And what numerics says, it's about 0.57 as far as we can tell. But we don't know how to prove that number. What we can prove is that 0.57 is between 1.5, basically. Let me show you the trivial bounds. The fastest that this thing could possibly grow is linear. If you take n disks, the biggest that you can make the diameter is just to line them up in a row. There's n of them, and they're each unit disks. And so when you have n of them across, it's 2n. The diameter of the disks are, if the radius 1, the diameters are 2. So that's the biggest it could possibly be. Okay, everyone agree with that? Okay, what's the smallest it could be? Well, if you have n disks, and you put them into a disk of square root of n radius, the area of this disk, well, the area is pi r squared. So if the radius is root n, the area would be pi times n. And each of these is a unit disk, so each of them has area pi, and they're disjoint. And how many unit disks can you possibly fit in to a big disk of radius pi n? Well, at most n of them, because the areas add up. And so the thing has to grow faster than square root of n. Okay, it can't grow slower than that. So we have a lower bound of a half and an upper bound of 1, and those are completely trivial. Can we improve those? Well, actually, when I was a graduate student, I proved an improvement of this. I got a better result. But Harry Keston, a famous probabilist, he got a better result. He proved the upper bound it grows at most like n to the 2/3. Now, we're not saying it's equal to that. We're just saying it's less than or equal to. The diameter is less than a constant times n to the 2/3. And I can give you a very brief sketch if you have a little patience of how this goes. You're going to have to take a lot for granted because I'm teaching a graduate course next spring, a topics class in which I'm going to go actually give the rigorous proof of this. It's one of my goals for that class, is to rigorously prove Keston's theorem. But here's sort of the sketch. Suppose that we have the cluster. It looks something like this. And it's already grown to be size m. That's the current diameter is roughly m. I want to ask, how long does it take before it grows to be size 2m? How long does it take to double in size? Okay. Now, we have to use something. And what we're going to use comes from complex analysis. That's why I mentioned that harmonic measure is connected to conformal mappings, because almost everything we can prove about harmonic measure comes from a theorem about Green's functions or holomorphic functions or something analytical. So we use a lot of complex analysis in this kind of theory. And there's a very famous theorem of Arne Borling. Arne Borling is one of the most famous complex analysts. He's probably not famous outside of complex analysis, but he's certainly one of the best known of the complex analysts of the 20th century. In fact, it's a trivia question. Albert Einstein was at the Institute for Advanced Study for many years. And when he left, who got Einstein's office? Who inherited Einstein's office? And the answer is Arne Borling. Arne Borling moved into Einstein's office when he was finished with it. One thing that Borling proved was that if you have a connected set in the plane, some set K, and its radius it's about diameter r, and let's just take a piece of it, which is diameter 1 in size. So r is big, maybe r is like 1,000. But we're just taking a piece that's about diameter 1. And now we send one of our Brownian particles in from infinity. It could hit anywhere. Okay? What's the chance that it hits this set of size 1? And what Borling said, well, it's pretty small. If you have a big set and a small piece of it, the chance that you hit that looks like 1 over the square root of r. Okay? And this is actually a sharp estimate. You can prove that if your set is a line segment, it say goes from 0 to r, and you just take the part of it going from 0 to 1, the chance that you hit that piece at the end is actually approximately 1 over root r. And so we can do this because we know how to map the outside of a line segment to the outside of a disk. That's an explicit mapping. There's a formula for it. And so we can calculate the harmonic measure in that case. And then what Borling said is that he was able to prove that's the worst case, that anything of that diameter will give you the same estimate. And what Keston observed was the following. If I have my cluster and it's grown to size m, what do I have to do to make it go from size m to size 2m? I need to build a chain in my cluster. So I have these chains of disks, but I need at least one of them to cross this annulus from m to 2m. To do that, I need at least m of these, okay? Because each of them is unit size, 1, 1, 1, 1, 1. So to go from m to 2m, I need m of them. When I have a disk, the chance of hitting it is about 1 over root m. That's what Borling says. You have a unit disk on an m-sized object. the chance the disk comes in and hits that one is only about 1/√m. Mostly it will land someplace else. But approximately every √m times I throw a disk in, I will hit the disk I want. And then if I wait another √n times, I should hit that disk. And if I wait another √n times, I should hit that disk. And so after I've waited √m times m, which is also known as m to the 3/2, enough time should have passed that I will have formed a path to do that. And if I have to wait that long, if it takes time m to 3/2 to grow that much, then I can, doing some arithmetic, I can prove that the diameter is growing at most like the number of disks I've thrown into the 2/3. So 2/3 is the reciprocal of m to the 3/2. And so this was Keston's argument. It's not a rigorous argument the way I presented it, but it is it's pretty close. Bernings' estimate said that the line segment was sharp. That gave us the best harmonic measure estimate. But DLA never looks like a line segment. It always has these other hairy figures. So we should get a better estimate than we should get something better than 1/√the radius. Because we know that the 1/√of the radius works for line segments, but for things that are not line segments, we should do something better. Been thinking about how to do that for 30 years now, unsuccessfully. So Keston proved his theorem around 1985 or so. It was the time I was a graduate student. And still, every few years I stop, take a few weeks and think about this, still haven't seen a way to improve Keston's estimate. But it must be improvable. We're absolutely positive it's improvable, but just don't know how to do this. Not just me. This is a famous problem. Stas Smirnov has worked on this. He's another Fields medalist in this area. And this is like one of his favorite problems. And he can't do it either.
What makes you so confident about that?
Sorry, there's a question?
What makes you so confident that it can still be improved?
Because I've worked on a lot of other hard problems, which looked like they were impossible, but they end up getting done somehow. Also, it's fairly easy to prove Keston's estimate. It's not tremendously hard. It's a little bit hard to give all the technical details, but basically a simple idea works. And it works assuming that the cluster shape gives us the same estimate as the worst case, which is a line segment. And the cluster is clearly not a line segment. We just need a way to quantify that. So DLA, so what we need to prove is this, that the DLA cluster is not equal to a line segment in the limit. No picture of DLA that we have ever seen has ever looked like it was approaching a line segment in the limit. So yeah, we must be able to do this. If not us, our students or our students or our grand students or somebody will figure this out. I mean, I feel pretty confident that this is a doable problem. So I've been speaking for almost an hour. I had about 5 minutes of more slides left. Should I continue with that, or would you like me to finish here?
Yeah, if you would like to continue and finish the talk, we can go another 5 or 10 minutes. Yes.
Okay. I just want to talk about the other bound. So the worst upper bound was the linear bound when they all lined up. But we said, well, we can do better than that. We can take n to the first power, and Keston showed us how to get n to the 3/2. So he was able to do some estimates which show actually can't. The DLA clusters will never line up like this. That has very, very, very low probability, vanishing. What about the lower bound? The lower bound said, well, if you have you need at least √n, because you can't pack more than, n disks into a big disk of radius √n. That was just an area comparison. That was a pretty easy argument. Now, there should be some kind of Keston-like argument to improve that trivial bound, right? But there's not. We know nothing better than √n. That is absolutely the state of the art. So if you understood the fact that you can only put n disks into a disk of radius, you can only put n unit disks into a disk of radius √n, your understanding of the problem is as good as any Fields medalist. That is all that we know, is that argument for a lower bound. We conjecture, of course, that it's going to grow like n to the alpha, where alpha is some power strictly bigger than 1, like maybe 0.57 or bigger than 1/2, 0.57. We can't prove that. We would be I mean, it would be the highlight of my career if I could prove the diameter of DLA divided by root n went to infinity. So just that it went a little bit faster than square root of n. Even that I would be tremendous. I could publish that in the best journal in the world if I could prove that, I think. Now, it always depends. If it turns out to be really trivial, then it's not so impressive. But so many people have thought about this for so long, I don't think it can be trivial. I think someone, I forget who, even offered a prize to prove that it's bigger than, say, 1,000 times root n. Not even going to infinity, just prove it's bigger than a big constant times root n. Don't know how to prove that. And so, so we're kind of stuck here. What we'd like to do, basically, is we want to show that the thing grows at a certain rate. So the enemy here is that when we grow the DLA cluster, it basically looks like it's filling in a disk as densely as it can. When we draw it on the computer, that's not what happens. When we draw it on the computer, there are these big gaps that it leaves open, okay? We want to basically prove that those are really there. So what we're trying to prove is that if we take the DLA cluster, and here I've drawn its convex hull, I've drawn this blue curve going around as the convex hull, we basically want to prove that the area of the disks is a tiny fraction of the area of the convex hull, that mostly it's white space, okay? And when I look at this picture, it looks to my eye like it's mostly white. Maybe it's 5 or 10% black and red. We want to prove that. That's the thing we'd like to prove, is that when you take this cluster and you draw, you know, a disk around it, you draw its convex hull, that mostly in the limit, the DLA cluster is taking up less and less of the area. It's leaving big white spaces in here, which are never going to get covered.
Can
Now-
I ask a question?
Yeah, go ahead. Ask the question.
All of these pictures is an artifact of using discrete things to approximate continuous motion?
Possibly, although I have been careful here to use, I'm not walking on a lattice. I am using steps on a circle and a random number generator to machine precision. So I'm doing my best to approximate an actual Brownian motion. There are hundreds of papers, maybe thousands of papers on DLA in the physics literature mainly. And I think everyone is pretty confident that this is what it really looks like, that it's not an artifact of the numerics. I don't have a more convincing argument, and I don't have any kind of proof of that, but I think everyone believes that the pictures are accurate. Okay? Now, one way we could prove that the DLA is growing pretty quickly is if we could somehow show that we're more likely to add disks to the tips and less likely to add them on the inside. Okay? And from our experience about conformal mappings, we know that if we have this convex hull, this curve that basically is a rubber band wrapped around it, at a place where there's a corner like this, notice that there's almost a 90-degree angle here. These angles, remember, collect harmonic measure. Harmonic measure likes to land on the corners. So places like this should collect more harmonic measure than the flat areas collect. Now, if you hit one of these flat areas, you sort of go inside and then you continue. So one thing we would like to prove is that when we draw the convex hull of a DLA, that there are some big angles in it. If we could prove that, that would be terrific. I don't know if it's true, but we can conjecture that. We can conjecture that if we draw the convex hull, then there are always some angles which deviate from 180. So 180 would be a flat line. What we'd like to somehow make a careful conjecture that there's always a few angles in here which are not too close to 180. They actually make a sharp angle of some sort. Don't know how to prove that. That would be terrific if we could prove that. In these pictures, I should mention, the difference between a red and a black is if the particle was added when it was on this convex hull, when it was the tips of one of these filaments, I colored it red. If a particle was added when it was inside the convex hull, so it penetrated like that, it was colored in black. And so the red ones are the ones that were added in this way I'm proposing, that when they get added as a vertex of the convex hull. The black ones are the ones that were added by penetrating into the interior and then being added. If you can prove anything about the relative fractions of the red and the black, like the black goes to be 100% in the limit and the red goes to be 0%, or vice versa, or anything, that would be worth knowing. We don't know that. One way that there might be angles in this convex hull is if there weren't too many vertices. If you have a polygon that only has 4 sides, for example, you can prove there has to be at least a 90-degree angle. So if you know that you have an n-gon, then there always has to be an angle of 360 over n. So one way of proving there's a sharp angle would be to show that there's not too many vertices. And so, of course, I did a computer experiment to count how many vertices the convex hull has. And it looks like to me, it looks like a logarithm function. And in fact, when you plot it on a linear log scale, it looks like the number of vertices is 2.2 log of n. It looks like a multiple of log n. Don't know how to prove that. Another open question. The enemy is that the DLA looks like a disk. So here I pretended that the DLA was a disk at some stage, and then I started sending the particles into it. And after about 1,000 or maybe 10,000 particles, it looks like this. So it's still pretty circular, but you see it's starting to get a little fractally on the edges. And when I maybe send in 100,000 particles, it looks like this. And to me, it looks like it's forgotten that it was a disk. If I were to cover up the middle here, sort of scratch this out, and just look at the ridge, the outer part of it, I couldn't really tell if it was starting from a disk or starting from a single point. So if the DLA, at least numerically, if the DLA ever did look like a disk, the enemy to us, it looks to me like it should diverge away from that. It should start to look like a regular DLA and have these big omitted disks. It leaves out these big spaces here and here and here. That's what we want to prove. We want to prove that as the DLA grows, most of the plane is not covered. That's the conjecture. But we don't know how to prove that. And so that was the last thing I was going to say today. So thank you very much for listening. I hope it wasn't too much too fast. But it was fun anyway. So I hope these are some of my favorite problems. And I have to limit the time I think about them. Otherwise, I would never write papers. I have to occasionally think about things which I think I could do. These I have failed for many years to do. Thanks.
Have you ever looked